let's get started again. Actually, I have very interesting information about the exam. So the exam is going to be very hard. No, but the exam is going to be very easy, and on the 17th of January, actually. So 17th of January will be the final exam. Then. Okay, so we had some good discussions in the break on these two goals. Like one goal is to have a large margin, to be very sure, right? Have a classifier which has a big margin, so you would change a lot, such that you would make it misclassify something. And then there was this other goal of just minimizing the cost, right? So we want both. And actually we had kind of two things on the first formulation we saw. We had minimize the cost, that's the sum on the left. And we had minimizing this norm, which is still a bit unclear to us. What is that going to be? What's the interpretation of minimizing the norm of W? And we're going to see this at the end, hopefully, once we have derived the dual problem. We will see that the second part is actually going to be the same as finding the classifier of the biggest margin. So we have this trade-off of the two goals. Okay, so that was the intuition, right? Left is a very good W, right is a bad W, and actually both of them have zero cost. The left one has 0 guys inside the margin, and the right one also has 0 points inside the margin. Both of them have 0 cost, but one of them has a very bad margin, the one on the right. And yeah, we discussed these cost functions quite in detail. So yeah, duality, that's where we were. So we had the left problem was the problem I just showed. Now we are in the process of deriving the right problem with these alphas. And then we're going to see if that's going to be a easy or hard problem. Okay, so yeah. Let's continue here. So we took one element, one data point, and we had a hinge loss for the 1 point, and there we introduced one new variable. Then now it's very nice because we have this inequality here. Sorry, this equality. So that's what we proved here, right? Good. Now, why is this useful? So now I will do nothing actually, just doing this for every variable here, right? So we did it for V, but in fact V is this complete thing which we had, the hinge loss of one data point, which is 1 minus the prediction, right? And then only the positive part. Okay, so do you guys believe that this is actually true, that the entire hinge loss now with this trick is going to be always the same as what we have on the right, which is now same quantities, but there is a new part. This new part is the alpha, but the value of the whole thing is the same, yeah. So now one number, we have actually made our life harder. We have written it as an optimization problem over new variables. But we said it's kind of what we want to do anyway, because yeah, we want to introduce new alphas. Okay, now this is for 1 point, and now let's do this for all points. So which is here. So every element in the sum, we're going to do this trick. Then all these values will actually be the same, right, by our equality here. Nothing has changed. But this only works if each alpha is maximized over the interval 0, 1. So what's this thing here? So that's just notation. Yeah, you can imagine what it means. It's so for each alpha n, it needs to be in the interval. That's the interval to the nth power, right? So anyway, so for each n. So that's a constraint. Each of them is constrained, and each of them needs to be maximized. Then this is really the same thing. So it doesn't matter if you do this maximization before or after the sum, right? Because each of them only concerns a very particular value, right? Each n has their own variable, and each of them needs to be maximized over the 0, 1 interval. And if we do that, we can use our yellow equality. So we know that nothing has changed. We know that the big thing here, okay, this value here, whatever. Okay, sorry, let's write differently. The entire thing, so this is going to be unchanged because of our equality, so nothing has changed. Any questions on this? Yeah, is it differentiable? I didn't say yet, but it's written there, yeah? So, okay, so differentiable, the question is over the W's or the alphas. And, okay, so, yeah, I should be careful. You're right, so here it's, you're right. So we have to be careful here. It's differentiable over, let's see, over W? No, right? Because it's the same thing as we had before. So. I don't, okay, is it differentiable over W? Okay, let's go slowly. So over alpha, it actually is, right? Do you guys agree? So, okay, fix W, now differentiate with alpha. It's fine, it's differentiable, okay. Now, what about over W? Actually now this strange point, the case distinction is now disappeared, right? So actually for a fixed alpha, this stuff here is actually differentiable for W. So here it actually is also differentiable with W. So for fixed alpha, yeah. But let's see, we jump ahead a bit. So the question is now, in which order do we do this W and alpha optimization? So that the question we're going to see which order is going to be better. Okay, but what's true anyway? If you look at this G function, then the G is actually, we can say this already now. The G is differentiable in all cases. So if you fix alpha, it's differentiable with W, and the other way around. So that's actually one reason why it's a bit nicer than what we had before. So that could be useful. We're going to see. Okay, what about the convexity? So yeah, because it's the same as we had before. The purple thing is the same. So the original thing was convex. So this is still convex in W. And actually, you can check that this is actually concave in alpha, which concave. What does it mean? It just means that minus this thing is convex, right? So. Yeah, sorry, this looks a bit complicated, but let's just summarize what we have done. We have done a bit of a trick. So we had this hinge loss function, right? And we found this trick with the interval, which kind of fell from the sky, but it turns out if you do this interval trick introduce a new maximization variable, the thing stays the same. And there is actually a more general formulation of this. You can do this with all functions which are convex and go from numbers to numbers, right? That's what we did here for this positive part, the hinge loss actually. So that's called is the Fenchel duality if you want to look it up, but we don't need it in full generality here. It's fine for us to have it in this example. So anyway, then mathematically, the new problem we had is exactly the same as the old one, as long as the alphas are maximized, right? That's what we proved. So nothing has happened. But now we can look at the G function, which now depends on the two variables, the new and old. And it turns out, yeah, that's a bit of a saddle point formulation now. First variable we try to minimize, second variable we try to maximize. So that's how it looks like, right? So if you visualize it, so here on the vertical axis you want to visualize this G function of W and alpha. And it depends on two things. So let's say in the easy case, when these are actually numbers, then turns out this G function was convex in W, because even the original function where we started from, that was also convex already. And it's actually the opposite, it's concave in these axes here. So right, if you fix W, look at what's happening with respect to alpha, then it's curved this way, so it's a concave function. And whenever you fix alpha, then turns out it's convex here. So that's roughly how this thing will look like. Okay. Now, so we finished the first part, so how can we derive such functions? So, and again, if you want this in full generality, you need to go to this thing on Wikipedia, or actually this interval thing is called the conjugate function of the hinge loss, which is our original function. So this can be done for more general functions, but here we don't need that for the moment. But the concept is very important, that now that there is this saddle point formulation, that it's like a game, right? There's one player tries to minimize, that's the W player, and then there is this other player which controls the alpha variables, and that player is trying to maximize, right? And they interact with each other. How do they interact? Well, just with this G function which we defined, and that's actually where this duality is, right? We introduce these variables just to be multiplied with our loss function per point, actually. That's how the two players kind of come together. But that's not even that important, but what's important now is that we're going to switch the order of the minimization. So, okay, so we said this G is convex in W, and we said it's concave in alpha, fine. We're not going to prove this, we don't specialize this far here, but you can believe that if this is the case, if this assumption holds, and if you have very weak additional assumptions, then you're allowed to do this switch. So by allowed, I mean, then they are actually the same, right? To first do the inner maximization over alpha, and then W is the same as on the right side, where for, fix alpha, you first do this inner minimization over W. So that's going to be the same. So now we're going to exploit this, and we're going to actually solve the problem on the right, instead of what we did before, which was doing gradient descent for W, which was just solving the problem on the left. So, okay, let's try to solve the problem on the right, which is what we had on the previous slide, right? But just the min and max we now change the order. So that's what we had, and now we're going to change the order of these two guys, right? Okay, let's try to do this. So here is really the same formula as we had before, but that's what we have done, right? We have switched the min and the max. So this is what we got then. Okay, and now we're getting to the interesting point, like how these two things actually relate to each other, and then how we're going to solve this new problem. Okay, so how do we solve optimization problems in theory, like when we try to really explicitly find a solution on paper? What do? We always do the same trick. We just set the derivative to 0. This actually is true for unconstrained, for every unconstrained optimization problem. This is the optimality condition is a very good idea, because then you will know that this is going to be a local optimum for that problem, especially if it's a convex problem, right? Which this thing here is. This is unconstrained and it's convex, as we said before. So I'm talking about the inner minimization problem. Just let's do it step by step. So we are now doing the inner minimization. So to forget about alpha, they are fixed for now, and now we're going to solve the inner one. And that, again, is going to work quite nicely with just setting the W derivative to 0. So let's see what we get from that. So doing that is called the first order optimality condition for this inner problem. So this is not so hard. Actually, we discussed this already. It's a nice problem because it's differentiable for fixed alpha at all points, so which is very convenient. So we don't have this problem anymore. Forget about these subgradients and stuff. This is all automatically taken care of here. So because it's just nicely differentiable now. There's no case distinction anymore. So this complicated stuff, that's all magically put into these alpha variables. They take care of that, right? But we don't care about them at the moment. We fix them and only care about the inner problem. Okay, so the inner thing has a very simple derivative actually. So what we want to do is we want to take the W derivative. So let me look at one entry of this sum. Let's see where does it depend on W. So the sum stuff is depending on W only when the linear prediction happens, data times W. And then there is a squared norm, but that's also very easy to take the derivative of. So here is the one from the square norm, that's easy. What happens for one of the data terms? So the derivative of this thing is just the data itself times the alpha times the y, right? So do you more or less agree with me that, so the blue guys, so minus the blue thing, that's going to be the derivative of the W from the sum. So this thing here then. Okay, or okay, now we got both derivatives. So now we set the whole thing to 0. So yeah, this thing now we set to 0. Yeah, what does this give us? Yeah, so you just solve for W. So it gives us that the W is actually the sum of these blue terms. So And yeah, we are already done. So that's what we have written in the next equation here. So we said we are given some fixed alphas, and we asked, can I magically, can I have a closed form solution which gives me the perfect W? Here it is. For any given alpha, that's the best W. We actually write it in matrix form. The very usual thing, you know that every data point is in a row of the big X matrix, right? So yeah, so the X matrix contains the data points as rows. So here's the first data point. Yeah, maybe it's a row vector, but it doesn't matter. And then the last row is the nth data point, and there's some more. So that's the X matrix, as usual, the same as in regression. Okay, then here is some special notation that the Y, I just write them into a diagonal matrix, the labels just for easier notation. So the Y is this simple diagonal matrix containing the labels only. Okay. So you can convince yourself if you take this data matrix X, you multiply with this diagonal matrix, then what happens? It's just every data point gets multiplied with its label. So that's all then. Right, so here the data points are columns because it's transposed, right? And then it's multiplied with the diagonal matrix entry, the corresponding one. So each column becomes what we had here. That's what we want, Y times X. So, and then they're all summed up with the alphas. And that's what happens when you multiply with alpha in the end. So just rewriting this is an easy way. Yeah, how do I get my W now? So just multiply with the data matrix. Any question on this one? Okay, so now we almost have the dual problem. So now we can do this for any alpha we want. And then here it is. So we started from the original problem here, the inner problem, but now we solved the inner problem. So now let's plug in what we have obtained for W. So the yellow values are now going to plug in this formulation. So yeah, here are they. So this is the yellow value, basically. I forgot the lambda. So, okay, so here is what I plugged into the regularization term, so W squared, right? And on the left was plugged into this guy here, right? Okay, this can be simplified a little bit because you will see that the two yellow terms are actually the same. So when this gets summed again over alpha, then you're going to get another of these W's. So like the yellow one is already a W kind of, so. And this is also W. And now when this stuff gets multiplied with this, then you get another W kind of. Okay, so then what we get is, yeah, the yellow stuff is getting in there with a minus. The yellow stuff times itself. and then you get the same term again with 1/2. So what remains is the minus 1/2 times this yellow stuff with itself. That's the idea. Sorry, might be a bit confusing, but nothing has happened, just simple computation. Then this one here is just a vector containing all ones. That's taking care of this term here. Okay, what has happened now? The inner problem has gone away, we solved it. The outer problem is going to stay what is written on the last line. And this is the dual optimization problem for the support vector machine. So, was there some unclear steps in the derivation? Don't hesitate to ask. Okay. Okay. So now we have this different problem, right? So this is now the left one we had before, and now we have derived this one. Okay. Now why is the new one better? So, or is a question? Yeah. Sorry, which term? The regularization term. That's this one here, right? It's the yellow stuff squared. So. Yeah, sorry. So this is W square norm, and that's actually the same as W. Sorry. So what this is norm of W squared. This is the same as W transpose W. And in the next line, I've written everything in transpose form, right? The vector transpose itself. So this thing is W, and this thing here is W transpose. That's the idea. I ignore the lambdas now, but you can take care of them. So. Okay, another question. So why is this better? It's actually, the nice thing is this differentiability problem is now disappeared. What we have on the last line is a quadratic function in the alphas. It's very simple, it's very smooth. There is no crazy point where it's not differentiable. So this is a smooth convex function, very nice. There is a different aspect, which is this aspect here. So that's different from before, because now we have a constraint. The alphas must lie in this box. So every alpha coordinate is restricted. This is 0 and 1. And yeah, if you compare to the original SCM problem, that was a bit different. There we had an unconstrained problem, right? Just minimize this thing over all W's. But there was a problem that it had this non-differentiable point, which you had here, right? So that was problematic. And it turns out you can have like either or. So now everything is nicely differentiable, but it has become constrained. It has become 0, 1 constrained. Okay. Other comments on this? So I claim that this one is actually much easier to solve, and we're going to see now next some algorithm to solve that. But before we talk a bit about how to interpret these alphas now. So then yeah, this brings us really to the third question: is it now easier or harder? So, and again, this is what we just said. It's now differentiable, which is nicer than before. There is a disadvantage. It's now a constraint problem, which we have here. but it's differentiable, which is very nice. So. Okay, later on, the algorithm which you're going to see, which will make it easier to solve, is coordinate descent. It's quite easy to imagine what it is. It's even easier than this stochastic gradient or something. So what it means is just you don't care about all the coordinates, but you only care about one. So the others you ignore for a moment, but one of the coordinates of alpha, you optimize it. And then you pick the next or another one. So that's coordinate descent, and this we're going to define it more precisely in the last few minutes. And yeah, you can implement it in the lab this week for this example. So, and again, the structure of the problem is quite simple. It's this matrix here, the Q matrix, which is what we had before. It's like the data times itself. So it's a quadratic problem in these alphas. It's not too bad. This linear term here also is quite easy. But you have to respect the interval constraints. Don't go below 0 and don't go above 1. Yeah, this matrix, it has some additional nice property which we're going to talk about on Thursday. So this is, so what you can do is you have used your original data here, the X matrix, right? X matrix times itself, right? That's, I mean, it's not clear why that would show up, but anyway, that's the matrix which defines your optimization problem. It actually was the same matrix also when you did linear regression. Well, sometimes it's the other way around. Sometimes it's X transpose times X. Now today is X times X transpose, which is, so if you have that matrix, then what this means is these were your original features. But now, what if you would derive different features and use those instead? What we have here is that the whole problem just depends on these inner products of the data points. Why? Yeah, so I mean, this will come next Thursday, but the X matrix here contains your data as rows. So what is this K stuff? That's a bit strange, right? Can look at, let's look at one entry. That's the I's data point multiplied with the J's data point. So. Right, so you've chosen some particular features for these points, and now you're going to use them. It's fine if you only compute this K matrix, because then your optimization problem is given, it's defined. So what this trick means, the kernel trick, which we discussed on Thursday, is that you can use different features. So there's some crazy transformation which could have happened on your data. And the trick is that you don't even need to know what this transformation really does to each of the features. You only need to know what it does to these pairs, right? So what it does to a pair of two data points. If you know that, then you have defined a new K matrix. That's kind of the similarity of all these points to each other. And whatever such matrix you have, you could just plug it into the problem here. And then, yeah, solve for the alpha for that. And that's what we're going to do next Thursday, this Thursday actually. And this is a nice trick, because in the projects you maybe saw that it's quite important to do good feature engineering. And this is a bit a more theoretically motivated way to like automatically produce kind of new features. So, but do it by hand also works very nicely, and sometimes even better than this, but this is a nice concept which will come later. This you cannot do in the original problem, but here you can do it because your problem only depends on the inner product of two data points with each other. Okay, another benefit is that many of these alpha variables will actually be 0 at the solution. That's very beneficial because if they're 0, we can forget about their corresponding data points. So that's we're going to see on the next slide. So there's some benefits from this formulation. So let's see what they actually mean. So and now again, like when they're 0, for example, does it mean anything? Okay. So let's start with the alpha equals 0 guys. What does it even mean? So, and actually these are called the non-support vectors. So you can imagine eventually now on this slide we're going to get to the name of this thing. Why is it called the way it's called? But let's start with the points which are okay, which are completely correctly classified, like this guy, for example. So what is happening with this point? It's outside the margin and it's on the good side. So its cost in the hinge loss is nothing. It's for free. This is a good point. This is a non-support vector, so its alpha is actually 0. So what that means is it's quite convenient. So if we knew that this is the case, we could completely forget about the point because its contribution here is nothing. It does not. Each alpha n here. So, right, this is going to happen actually. Yeah, the xn is going to be multiplied with its label with alpha n. So if alpha n is 0, they just disappear. The points have no contribution, and you could just remove them from the problem. So you would not even need them for training. The problem is you don't know. At the beginning you don't know that at the solution they're going to have this nice property. So that's the non-support vectors. So actually what I'm doing now is just the same case distinction as we did before when we actually defined this thing, when we defined our trick. So now I did the case when you're at the border, at the constraint of the alpha, which means that you're in the middle at the 0 cost regime for the hinge loss. Okay, then here is some more interesting point, which is the essential support vectors. So here is one of these points. And in that case, the alpha can actually be many things. It can be anything between 0 and 1. So what I mean is, these are the points which are exactly at the point where you start to pay. So actually here. So okay. So here if our points are here, then we have f equal 1. So that's what it means to be 1, right? You're on the margin exactly. So if you are at that point, it means you're essential support vector. It means, so that's the second case when the alpha variable can be anything. So. And okay, let me finish the first case. So the first case is, we said, when you're on the good side, like here or here. So here you pay absolutely nothing, right? So that's case 1. Here, case 1. 0 hinge loss cost. And now this is the blue case, is the borderline case, which actually rarely happens. So if you're confused about the blue one, then let's do the third case first, which is actually the most important case, where the cost actually appears, right? So where there's a non-zero cost. This happens, for example, when your f is here. So f is maybe 0.3, whatever. Then you have to pay, but you don't pay so much. And then if f is even stronger on the wrong side, so then you pay more, right? Okay. These are the bad points. For those you have to pay. This is actually one of them. It's not so bad. And here is a, so yeah. This one would be even worse. And here you really have to pay. Sorry, I redefined this point here because I'm only talking about red points. So, okay, so there's two red points which are actually in the margin or on the wrong side. For those we pay. So, and these are called the bound support vectors. So, and that's case 3. All right, so the same case distinction as we've done before. And there are the 3 cases that can happen. So why is this thing called the support vector machine? It's because of that, because the whole thing, the classifier is defined by only the ones with the non-zero alphas. Because the ones with 0, they have no influence. But the support vector points, if you knew these, then you could just train on them. You would get the same classifier. But you don't know at the beginning, so you just train on all of them. But once you have trained, you can remove them. And that's something you don't know if you only do the the original problem. But this is some interpretation we gained now additionally by taking this dual view. So now this is the information that the alphas carry. So in general, this might depend on the problem, but for the SVM, they carry this information because you can just look at the case distinction of what can they possibly be. All right, so we are almost done. We have 2 minutes, that's perfect. So what's the algorithm? And as I said, it's basically described in 2 words, right? How are we optimizing this problem now? It's very easy. You fix all alphas except 1. So now the one I'm going to actually look at is alpha 2, say. So I'm going to optimize just this direction. I started here. I'm going to move up and down. So where I'm going to move? I'm going to move here to the lowest point. So this level sets here is indicating where is my objective function the lowest. Let's say you want to minimize something. I want to go to this alpha star. No idea where it is, but I'm just doing it step by step. Only optimizing alpha 2 brings me here. And I pick a different coordinate. Here there's only one different one. I'm going to optimize alpha 1 now. If I move on this line, the lowest point I can get is here. So now I pick a different coordinate again, move up and down. I'll go here, then I go right. And I'll do this staircase thing. And I will slowly go towards the optimum. That's what coordinate descent does. And you can do the same thing no matter if you want to minimize a function or maximize. It doesn't matter, right? You just do the same for minus the function. So, yeah, and that's what you can implement in the lab. And that's all I had this week for today. And here's the formal definition of it, but it's really just what we said. Nothing special to accept. Okay, see you on Thursday.